So in this video, we're going to be looking at acyl chlorides. Now, acyl chlorides themselves, they actually have a acyl group, right, where they've got a carbon-oxygen double bond and a variable R group itself. But directly attached to that carbon atom and the carbon-oxygen double bond, we have a chlorine atom attached to itself as well. Now, this acyl group, you've seen it before in aldehydes, ketones, esters, and acid anhydrides. But today, we're specifically going to look at acyl chlorides, and then we're going to touch on how to make amides itself as well. Now, an acyl chloride is an example of a carboxylic acid derivative, and that is a substance that we can make from a carboxylic acid itself. We've already looked at two other carboxylic acid derivatives, including esters and acid anhydrides, but today we're going to focus on acyl chlorides and amides itself as well, where you can see an amide is when we have an NH2 group directly attached to the carbonyl carbon atom over here. Now, acyl chlorides, how do we make them? Well, what we do is we take any carboxylic acid that we want. In this case, I've got propanoic acid, and we can react it with a reagent called thionyl chloride, SOCl2, otherwise known as succo. And what we can end up with is our acyl chloride. Look at the naming convention. Propanoic becomes propanyl, and then we end it in chloride itself. We form two byproducts. One of them is sulfur dioxide, and one of them is HCl itself as well. Now, moving on to the reactions of acyl chlorides. Acyl chlorides, they're very reactive towards nucleophiles, and normally what happens is the chlorine atom is replaced by an oxygen to form a ester or a carboxylic acid, or the chlorine atom could also be replaced by an N atom to actually form amines itself as well. Now, these reactions are classed as condensation reactions, but instead of making water, we actually make HCl itself as well. Now, the first reaction is when we take a acyl chloride and we react it with water to remake the carboxylic acid that we actually first used to make the acyl chloride itself. So in this case, you can see I take butanyl chloride, react it with water, I reform the butanoic acid itself, but this time I actually release HCl in this condensation reaction itself. Now, the second reaction is when we take a alcohol and we can react that alcohol itself with our acyl chloride to make an ester, and this normally actually produces a better yield than using a carboxylic acid itself. And you can see we've got butanyl chloride. This chlorine over here is going to be replaced by an oxygen, and we end up having two of our carbon atoms over here added on from our alcohol, and you can see we can make ethyl butanoate, but in this case, rather than having water being produced, we actually have HCl itself as well, right? Now, another thing that you need to be aware of is phenol. Now, phenol, although it's not an alcohol, phenol can actually undergo a reaction with your acyl chlorides quite readily, and it can actually do that to form a ester itself as well. And that's one way of making phenol-containing esters itself, or adding a benzene ring into your compound as well. Now, the third reaction is if we were to react our acyl chloride. In this case, we've still got butanyl chloride. If we were to react that with excess ammonia, we would make something called a primary amide itself, where our amide, right, in this case is going to be all of this bunch over here. We've got an NH2 directly bonded to a carbon that's also directly bonded to a oxygen with a double bond itself as well. Now, this is classed as a primary amide because the nitrogen itself is going to be attached to one carbon atom. Now, the reason why we actually react this with excess ammonia is because the first equivalent, you can notice we've got two lots of ammonia over here. The first equivalent is going to be used, of course, to actually form the amide itself, but the second equivalent is used to actually stop our amide from being protonated by the HCl that's produced, because normally we would end up producing HCl over here, but then of course we don't want that H plus there to be donated, so that we actually end up with NH3 plus on our amide. But instead, right, a second lot of ammonia stops that from happening, mops up the H plus and forms a salt with the chlorine itself as well. So you end up forming ammonium chloride as a byproduct rather than HCl in this reaction itself. If we were to look at the fourth reaction, we've got the reaction with a primary amine, and what we can actually make is a secondary amide in this case. Notice how it's different to the primary amide. A secondary amide has two carbon atoms attached to the nitrogen atom itself as well. But in this case, right, what we would do is we would react our acyl chloride with excess primary amine in this case, right? Now, an amine is basically a derivative of ammonia, where you've got one of the hydrogens swapped out for an alkyl group itself. In this case, you've got ethyl amine, right, and you've got two lots. One lot, of course, to actually form the secondary amide, which you can see we've got over here N-ethyl butanamide, and then another lot to actually deal with the HCl that's being produced, so we don't end up protonating our amide again. Now moving on, right, I've got a task for you to do. Feel free to pause the video and have a go at this summary synthesis map by adding the products for each reaction itself. So yeah, starting off, right, we've got our acyl chloride that we can see contains 2 carbon atoms, 1, 2. If we react it with water, we end up reforming the carboxylic acid, and then we also form in here as well HCl. If we were to react it with ethanol, right, which is an alcohol, think it's got 2 carbon atoms. Ethanol is going to look like this. We're going to end up with 1, 2 carbon atoms. We're going to end up swapping our chlorine with an oxygen so that we end up with something that looks like this. But then to that oxygen atom, we have 1, 2 carbon atoms attached, and that's how we make an ester. In this case, I've got ethyl ethanoate. Now what about if we were to add excess ammonia, right? Well, if I add excess ammonia, we know that we can end up forming an amide. So in that case, a primary amide, I end up with carbon oxygen double bond here, a bond to a nitrogen, and then it's just going to be NH2 itself as well. Remember, nitrogen is comfortable with 3 bonds. If it has 4, it's going to be positively charged. What about if we had excess methylamine? So methylamine is basically when we have 1 carbon atom attached to an amine group. So in that case, I end up with 1 bond and going from a carbon atom to NH2 itself. You could have also had in this case CH3 and then NH2 itself. Either one's fine. So if we were to look at what's bonded, then we've got an acyl chloride where our chlorine has been swapped out, and what we've replaced it with is a nitrogen itself. And again, remember, because you've got that methyl on there on methylamine, what you're going to do is you're going to put another carbon atom on there, and don't forget that nitrogen has 3 bonds itself. So in that case, you end up with the following structure, a secondary amide in this case. Now moving on, feel free to pause the video and have a go at the following more complicated synthesis map. So yeah, starting off with this then, right, we'll start off from the left hand side because that seems a bit easier. How do we make an acyl chloride, and then how can we go in the reverse direction? Well, we know we can actually take ethanoic acid, because in this case I've got ethanoyl chloride. I can take ethanoic acid and I can react that with succal or thionyl chloride itself, which is SOCl2. I can form an acyl chloride, ethanoyl chloride. Going in the reverse direction, I can react an acyl chloride with water to reform the carboxylic acid. That's one of our reactions done there, going both ways. What about if I were to react this acyl chloride, right, with excess ethylamine? Well, ethylamine is going to have 2 carbon atoms bonded to an NH2 itself, and it's in excess, so we know 1 is going to react with the acyl chloride to form the primary amide, and then we know another one is going to be neutralizing the HCl so it doesn't protonate our amide itself. So what do I end up with? Well, I end up swapping out the chlorine atom for a nitrogen itself, and that nitrogen has 2 carbon atoms attached to it, 1, 2, they're done, and then I'm going to have a hydrogen over here as well, so it's going to have 3 bonds. Remember, nitrogen has 3 bonds, the remainder is going to be hydrogen itself. What about if I were to look at, let's say, a reagent that could actually produce this secondary amide over here? Well, I've got over here 1, 2, 3 carbon atoms on my actual amine that's going to be used to make this. And so if I were to look at my amine, I'm going to need to use excess, of course, because we want to neutralize the HCl as well as make the secondary amide. And so what I would need is 1, 2, 3 carbon atoms, but then to the second carbon atom I'm going to have NH2 itself, right? Don't just put NH, it needs to be NH2 because hydrogen always has 3 bonds itself. If it has 1 more, it's going to be positively charged. What about the next one? If I were to take an acyl chloride and react that with something to make an aromatic compound A, in this case we would end up with a ketone. Think, how do you form a bond to a aromatic compound? Well, you come across this reaction before, where you react your compound, your acyl chloride, with benzene in the presence of a halogen carrier catalyst, which we're used to using AlCl3, aluminium chloride itself. And so what we end up with is a ring of benzene, which is going to look like this, and then to that carbon atom, right, we end up, of course, with Friedel-Craft's acylation. We have acylated this benzene ring, and so we formed a bond to the carbon oxygen double bond directly. But then remember, you've got 1, 2 carbon atoms over here, and so we need 2 carbon atoms over there as well. And there's the answers for that one.